Swayam Prabha. Digital India. Educated India.
So, last class we stopped and said what weightability is. Now, this one we should also describe that in some cases, as I said, there is a relative motion, right, between the solid and the liquid. Okay. So, we will try to understand why there is a relative motion and what governs the relative motion essentially. So, we are going to do spreading of a liquid on a solid surface. Okay. So, if we define something like a spreading coefficient SP, it is basically given by sigma SV minus sigma LV minus sigma SL. Okay. So, the spreading coefficient, this is called the spreading coefficient. Spreading coefficient, it is a measure of the ability of the liquid to spread over a solid substrate. So, if I define it, it is the measure of the ability of the liquid to spread over the solid substrate, okay, whatever solid substrate that we are speaking of. Okay. Now, in this same context, if it is liquid solid SPLS, we can substitute the definition, okay, of the relationship between the contact angles, and this is what we get. So, it is sigma LV multiplied by 1 minus cos theta. Now, for partially weighting liquid, okay, your theta, if you recall the definition, theta was always like this, right. Okay. So, therefore, this leads to cos theta is always less than equal to 1. So, therefore, this implies that this SPLS is always negative. Okay. So, liquid will partially weight and form an equilibrium contact angle, right. So, when it is negative, when this is negative, the liquid will spread and it will form a new equilibrium contact angle. Got it? Okay. So, this is the basic definition of the spreading of a liquid. So, this is the spreading coefficient. So, you can calculate the spreading coefficient, okay, and you can determine that whether it is positive or negative. Depending on if it is negative, the liquid will spread. Okay. Now, let us look at another interesting thing. Now, so far we have said that the phases are, you know, always separated, okay, by sharp boundaries. Got it? So, they are always separated by sharp boundaries. That is one of our assumption, okay. But in reality, most of the interfaces, if you look at it, interfaces are where the properties vary continuously rather than having a sharp jump, right. Okay. So, rather than having a sharp jump, the properties vary continuously across the interface. Okay. So, how some of these things happens, we will take a look and how that actually affects the corresponding adsorption, the corresponding weighting behavior, right. Now, one important phenomena that happens in these cases is that there is something called adsorption, and how adsorption plays a role over here we will see. Okay. So, say you have a solid and a liquid, there is an interface, okay, there is an interface thick or thin, okay. you can have a solid, liquid, gas, whatever is the other medium of the other phases. Okay. Now, what happens is that in some of these cases this interface retains the molecules of the other phase. Okay. So, if it is a solid, it retains some of the liquid. Okay. So, let us take an example that you have a solid boundary, there is a liquid over here. So, the solid interface, solid side of the interface basically retains some of the liquid molecules. Okay. It basically gets adsorbed on the surface. Okay. Now, as soon as it gets adsorbed, the liquid molecules, it affects the weighting behavior, right, because it alters the interfacial tension of the solid and the liquid interface, correct, right. So, the adsorption, what happens is that this layer that it forms, okay, where some of the liquid molecules are actually retained, okay, on the solid substrate, okay, on the solid side of the interface. Okay. So, this basically affects weighting, okay, since it alters the interfacial tension of solid liquid interface. Okay. So, the surface pressure, if we consider something like a surface pressure, how would you write it? This Ps will be nothing but sigma Sv, right, minus something like sigma Sv adsorbed. Okay. It can happen between any two interfaces, by the way. Okay. So, this is the additional surface, this is the surface tension with the adsorbed surface present, the interfacial tension with adsorbed surface present. In other words, it basically alters the pressure, the surface pressure. Okay. Now, if we take this same relationship and substitute it in our Young's equation, okay, what will happen is that sigma Lv, and this is an important relationship, cos theta is given by sigma Sv minus Ps minus sigma Sl. Okay. So, adsorption basically, now if you want to find out the cos theta, which is the equilibrium contact angle, so adsorption changes equilibrium contact angle. Okay. So, adsorption changes the equilibrium contact angle. Okay. So, if you can see this particular relationship over here, okay, so this actually shows that this is the revised relationship when you actually have this adsorbed layer which is present on the surface. Okay. So, based on that, it is very easy to determine the revised relationship, which shows that the equilibrium contact angle is supposed to change because of this. Okay. Okay. Now, having done that, now let us look at some of the behavior of these liquids, okay, the surface tension, the theta and the capillary pressure, etc. How do they determine the behavior of liquids in like small tubes or channels or porous media? So, if you have a tube like this, you know, or you can have channels, okay, channels drawn, okay, and it can have porous media, basically porous wicks, and you can have this kind of a meniscuses that will form. Okay. So, all these things we can try to look at it in some details over here. So, let us take the figure and how, let me draw it properly first. So, something like this. Okay. So, there is a capillary tube basically. This may be a little exaggerated. Okay. So, this point interface is marked as A, the equivalent point is marked as B over here. Okay. Now, this radius is basically given by small r, okay, and this this is the contact angle that it makes. So, this is contact angle, it's given by theta, okay. And so this is a point C on the and sorry, this is H, which is the height of this liquid column, okay. So, here if you recall, Ri or R1 equal to R2 equal to R cos theta, okay, because it is a very small tube, it is a very narrow tube, small diameter tube, and if you look at the tube, it has got the following: there is a height h, okay, there is this points A and B, it makes an angle with the wall which is about theta, and that point in the meniscus is given by C, okay. And so that is the rough configuration that we have, and of course there is the 3-phase forces that are acting on it, okay. Now, so therefore, PV minus PL capillary at C basically. So, the capillary pressure at C is basically given by 2 sigma by R cos theta, all right. Okay, it is given by 2 sigma by R cos theta. If it is divided, it is 2 sigma by R, R is given by this R by cos theta. So, you can imagine what it is. So, the pressure at the flat surface, that is the flat portion of the meniscus, at flat surface A is given by P A is equal to P V plus rho G H, right. The height of the liquid column is a vapor pressure plus that particular pressure. P B must be equal to P A because they are at the same horizontal level, right. So, from these two relationships we can get P B is equal to P V plus rho L G H, okay. The previous one was rho V, okay. So, rho L G H minus P cap C, okay. So, therefore, now 2 sigma cos theta by R is equal to rho L minus rho V, sorry, this is rho, this is not P, into G H, okay. So, you can imagine, so there is a simple capillary rise within this particular tube, okay. What we have done is that the pressure here is nothing but the vapor pressure plus whatever is the whatever is the vapor column that is sitting above it, okay. Then the pressure at PV must be equal to PA, right, because they are at the same horizontal levels, okay. And then it is just a matter of substitution, okay. And by substitution and doing the introducing the capillary pressure, we get this particular expression over here. So, this is the final form, okay. So, if your theta now is less than 90 degrees, what can happen? The capillary rise can be seen, okay. It can be seen. So, we will get a capillary rise, right. If theta is greater than 90 degrees, okay, the capillary rise H is negative, okay, and hence there will be a depression, no rise, there will be depression, it will not rise, right, okay. So, it cannot be seen, okay. So, when you actually have solid materials with respect to water, say for example, we can actually have two classes of substances, hydrophobic, okay, where theta is greater than equal to pi by 2, and you have hydrophilic, which we already stated earlier, now it is a formal definition, is less than pi by 2, okay. Where our hydrophobic substrates are used, there are plenty. You can have it for waterproofing, that means your waterproof, for example, that you wear, or windshield if you want to protect your windshield from the water, okay, and it can be also used for removal of water. Okay. So, if you want to just have water roll off, there are clothings which are also made in that way. It can be also removal of oil from water. Okay. So, you can use the hydrophobic substances for a variety of things. Okay. And this is an art these days. We can make hydrophobic substrates of different kinds. Hydrophilic on the other hand, okay, is basically a water loving kind of a thing. Okay. So, it is used as sealants, cleaners, surgical instruments, many other things. Okay. So, there are a lot of usages of the hydrophilic substrates. Okay. So, we have done what hydrophilic, hydrophobic means, and we have done also that how a liquid can actually rise and what are the things that actually govern the movement of the liquid, what is a spreading coefficient and things like that. Now, we will introduce a new concept over here which is valid for completely wetted surface, that means ultra thin films, okay, and this is called the disjoining pressure. So, let us look at ultra thin films and the concept of disjoining pressure. Okay. So, when a substrate, let us imagine a substrate like this. Okay. This is a substrate. There is a very thin layer of liquid which sits on the top of this substrate. There is a liquid film, and the thickness of this liquid film, the order of it is about 0.2 to 10 nanometer, very thin. Okay. It is not a very thick thing, it is a thin film. Okay. So, in this thin film, of course, the liquid molecules are very close to the solid substrate, right. So, there is a very strong pull of the liquid towards the solid substrate. So, the solid substrate basically tries to pull the liquid back. So, the solid substrate basically tries to pull the liquid back. Okay. So, this is basically due to once again the intermolecular forces. Okay. Now, if capillary pressure is say absent, let us look at the situation. If the capillary pressure is absent, okay, then the pressure inside the liquid film is changed by a very small amount because of this additional pull that is created by the substrate, correct. So, if capillary pressure, that means because there is no curvature, say for example, capillary pressure is absent, right, then the pressure PL, which is basically the pressure the pressure PL, okay, inside the liquid, okay, liquid film that is changed by an amount PD. Okay. This PD is called the disjoining pressure. Okay. So, thereby the PL is less than PV, the vapor pressure. So, PL is equal to PV plus PD, which is the disjoining pressure. Okay. So, this disjoining pressure is basically negative when the solid draws the liquid. Okay. So, this PD you can readily see it is a function of the intermolecular forces, okay, which is basically a combination of the dispersion forces and the electrostatic ones. Because as a combination of these two forces, okay, there is a depression, okay, of the liquid pressure, okay, and that is done because there is this disjoining pressure, which is a negative value, which basically makes the solid to pull the liquid towards itself, right. So, let us look at the presentation file now. So, let us look at this particular graph over here, okay. This is basically the disjoining pressure, okay, on glass at 77 degrees Celsius, okay, and this is of the order of nanometers, the horizontal scale, that is the thickness of the liquid layer. So, when it is about 5000 nanometer, which is basically 5 micron, you do not see any disjoining pressure at all, right, it is 0, practically non-existent, okay, and it shows this exponential type of a decay characteristics, right, where for example, when you are at 100 nanometer, the disjoining pressure is actually pretty low, right. It is of the order of somewhere around 40 kilopascals. Well, not low per se, but it is actually much lower than when you are going down to a very thin film limit of like 0.5 nanometer. It is very high. Very high means very high, like 100 kilopascals is 1 atmosphere. So, it is 4 times, okay. It is basically 4 times atmosphere, okay. This is for example, it is half atmospheric, okay, in these cases, and it is like 4 times to 5 times atmospheric conditions, okay, as you move one order. So, 100 to 10 you get an increase, okay, and from 10 to 1 basically you get a huge increase in the disjoining pressure, okay. So, this disjoining pressure is an interesting quantity, okay. So, let us look at, so this is one example obviously. Now, when we come across to our original thing, okay, we can show, it can be shown, and that would require a complete statistical mechanics course. It can be shown that the PD is a function of this thickness of this layer, is basically given by 2AH capital divided by pi n minus 2 n minus 3. Do not be bothered about these things, okay. N is the exponent of long range, okay, potential, okay. So, that potential can be something like this, okay. So, that is the long range potential. This long range interaction potential can be represented essentially by the Lennard-Jones 612 potential, okay, where basically your n becomes equal to 6. So, PD delta is given by AH 6 pi delta minus 3, okay. So, this is basically when you use the Lennard-Jones potential you get that, okay. So, Lennard-Jones is a 612 potential, it's very common in statistical mechanics. So, on the other hand, most common way of writing this will be minus A prime delta minus B, okay, where these depends on the molecular and electrostatic interactions, this A prime and B, molecular and electrostatic interactions, okay. So, PD is very high, since PD, so some of the characteristics is that PD is very high, okay, very high for ultra thin films, right, that we already got through the example, ultra thin films, right. So, it affects your liquid transport, okay, it affects your evaporation, we will see, and it affects of course the contact angles, okay. So, now, so this actually shows that PD is a very important parameter, especially when we go down to a very thin film dynamics. Okay. So, that would be the next, and if we look at a situation like this now, let us look at the presentation once again and pick the pen. So, let us assume that there is a thin film on a solid substrate. Let us pose this problem first, that what this problem essentially entails. Okay. So, there is an inclined substrate like this, inclined or whatever. Okay. So, this substrate has got a temperature of Tw, okay, and there is a liquid which is basically wets the surface like this before it goes and forms the principal meniscus over here, right. So, there is a this is very similar to the problem that we did when we actually had a wall and there was a thinning of the liquid, if you recall. So, it is very much similar to that, it is equivalent. Okay. Now, this region, okay, so it basically, this film actually wets the surface. If you look at it, it basically wets the surface, okay, and then it forms then the curvature increases and it flattens out. So, it forms that arc like this. Okay. Now, this can be divided into several parts, right. Okay. So, the liquid spreads to the wall to form an extended meniscus, that is the interesting part. So, here it is really thin, this region is really thin film region. This region is what we call a microfilm type of region, not that thin, but still thin enough. There is an intrinsic region, okay, and then there is the meniscus region. Okay. So, there are three regions: non-evaporating thin film, there is a microfilm, there is an intrinsic region, there is a meniscus region. Okay. So, thin film essentially starts from here, and microfilm also you can encompass it within the thin film family essentially, right. Okay. So, this is the nature and the scope of this particular problem, right. Now, in equilibrium thin film, okay, the liquid molecules adhere to the surface. So, therefore, there is practically no evaporation. Now, in the non-evaporating thin film region, okay, the temperature of the wall is basically imposed on the liquid, right, because the liquids are basically, liquid molecules are basically adhering to the substrate. So, in this region, okay, what we have in equilibrium thin films, okay, in equilibrium thin films, what happens is that the liquid molecules adhere to the solid substrate, to the solid, right. Okay. As a result of that, your Tw becomes equal to T delta. Okay. So, that is the interfacial temperature is equal to the wall temperature. Okay. So, there is practically no evaporation. Okay. Okay. Now, in the microfilm region, so in that thin film region nothing happens, right. Now, it is in the microfilm region where many things starts to happen. So, let us remove this so that we can write a few things over here. Okay. Now, in the microfilm region, okay, all the evaporation happens. Got it? Okay. The meniscus here in this region is influenced. So, the meniscus we can say it is a function of both the capillary pressure as well as the disjoining pressure, right. Okay. It is a function of both, and you can see that your saturation pressure is less than equal to the T delta, which is less than equal to the T wall. So, the interface temperature is not exactly equal to the wall temperature. Wall temperature is actually a little higher. This is because this is in the slightly thicker region that we are dealing with, right, and this is actually more than the saturation temperature. This we will show a little later what this exactly means. Okay. So, the flow in this particular region is driven by curvature, if there is a flow, curvature and disjoining pressure. okay, curvature and disjoining pressure. Now, subsequently as the thickness grows, right, as delta increases, okay, the disjoining pressure naturally comes down, right. Okay. So, in the microfilm region you actually have a flow and evaporation, and here both the curvature as well as the disjoining pressure plays a role. Now, here we have seen one other thing, that there is a change in saturation vapor pressure over a curved interface. Okay. Now, in thin films both PD and the capillary effect reduce the saturation pressure compared to the normal condition. Okay. So, in the thin film region the disjoining pressure, this is still the thin film region, right. So, the disjoining pressure as well as the capillary pressure effectively reduce the saturation pressure compared to the normal condition. So, in other words, there is a change in saturation vapor pressure across a curved interface, and in the thin film region the two main players are capillary pressure and the disjoining pressure, which basically reduce, okay, the saturation pressure compared to any other normal conditions. Okay. So, we will in the next class what we are going to do, we are going to prove that this is really true, and then we will work through the math of interfacial heat and mass transfer, including the effect of this disjoining pressure and surface tension and things like that, okay, before we move on to the phase transfer, that means how the phase transition happens. Okay. So, we will stop here in this particular class, we will pick up from this particular problem, and we will show that why there is a reduction in saturation pressure across the meniscus, okay, in the thin film region, particularly in the thin film region. Okay. So, so that is it, we will see you next class. Thanks.